Hi guys, welcome back to this experimental tutorial on Thermistor MOSFET Fan Controller. If you are here, I am assuming that you've watched part 1 and part 2 of this tutorial. If you have, this means you have a pretty good understanding of how this circuit operates and the various components we use to assemble this circuit, as it is very well illustrated here. In the other hand, if you haven't watched part 1 and part 2, I really recommend you to go and watch those tutorials. Find the links in the description box below so that you can see how we arrived to this point. Alright, before we move forward, I would like you to stop and do one thing. Click the like button and subscribe to CMTEQ channel, because there is value in this channel. You're going to get more tutorial like this, even better, deeper understanding of basic principles of electronics and electrical engineering. Thank you very much in advance. Okay, now we move forward. In this tutorial, we'll be focusing on the simulation and calculation on how to determine the value of this resistance here. This is the value of R1. That's the same one we have here, which is a 22K for our experiment. And this resistance actually set the point where this fan is supposed to come on. Now, let's say you want the fan to turn on at 60 degrees. So basically, if this NTC detects a 60-degree temperature, you want the fan to turn on. Not less than 60 degrees. Obviously, at over 60 degrees, the fan will be fully on. But how do you get the fan to turn exactly at 60 degrees? Now that value, that set point is set by determining the value of R1. Now how do you find R1? How do you get that value of R1? That's what we're going to see in this tutorial. So stay tuned, make sure you watch all the tutorial and you don't miss anything, because this is very important. Well, as you can see here, I have here a circuit that is wired in Proteus simulation, which you can download from the website. Now, as you can see, I have connected 3 voltmeters. That is this one, and this one here. So voltmeter 1 is across a thermistor, voltmeter 2 across R1, and the third one is across Q1. Okay? So as you know, in order to measure the voltage drop across a device, you have to connect a voltmeter in parallel with that device. I also have inserted into the circuit 2 ammeter. So you can see there's 1 ammeter that is between the power and the thermistor. So that's basically, because this is the power wire, so I basically cut here and inserted an ammeter at that point so I can measure the current flowing into the thermistor. At the same time, I've also inserted another current meter that is connected between the fan and the drain. So that must be this wire here. As you can see, the power is flowing like this. This is my fan connection. So at this point here, where the current is supposed to enter the drain, that's where I've placed my second ammeter so I can measure the current. Now you can quickly see that this ammeter is measuring microamps current and this one is measuring amps. So that basically means there will be more current flowing here than here. Okay, so right now when I turn on this circuit here, we can see the temperature is set obviously at 25 degrees and the fan is off. The fan is not turning. Why? Because the threshold voltage is below 4 volt. It is 2 volt, as you can see. Okay, and that is a 2 volt that is dropped across R1. And we have 10 volt that is dropping across the thermistor, NTC. This is clearly, this 10 volt is clearly the supply voltage minus the 2 volt that is dropping across the resistance, R1. So here, basically, we have a voltage divider circuit, which illustrates Ohm law. So we can see that the current meter that is connected in this series circuit here is reading 102 microamps of current at 25 degrees. Now by Ohm law, which is V is equal to IR, this means the voltage by Ohm law, which is V is equal to IR, means the voltage is proportional with the value of the current and the resistance. That is the voltage across these two resistance, the thermistor resistance and R1 resistance. Now, according to this thermistor's data sheet, it says the thermistor resistance is equal to 100 kilo ohm at 25 degrees C that we've set here. That is the ambient temperature. So if the resistance is 100K and we have 100 microamps of current flowing through, that means by ohm law, the voltage drop across it is going to be 10 volt. And that's a 9.95. We are getting there pretty close. And the same will apply to the voltage drop across R1, because you have basically the same current flowing through since it's a series circuit. And if 100 microamps of current is flowing through a 20K resistance, you're going to have 2 volt dropping across that resistance. So this is how the threshold voltage is set at the gate of this MOSFET right here, IRF 840. That is by varying the voltage drop across the thermistor, which vary by changing the value of the temperature. As you can see, if I start increasing the temperature here, that means I'm dropping the value of the resistance of the thermistor. Increasing temperature means decreasing the resistance. That means decreasing voltage, and increase in this voltage across R1. As you can see, that means the threshold voltage is also increasing. And you can see clearly that current is also increasing, because basically we have the total series resistance here is decreasing, so you'll have more current that will flow through that series circuit. These are basic principles of electronics. Okay, so please guys, you have to pay attention. So in a nutshell, the value of the voltage across the thermistor, that is your V threshold, is your V supply minus the voltage drop across the thermistor. The other thing I want you guys to observe is the voltage drop across the MOSFET and the current that is flowing through. As you can see here, the conditions are like the MOSFET is still off. It's not on yet because the fan is not turning. Now, as soon as I start increasing here, observe, as the threshold voltage get closer to 4 volt, boom, as soon as I reach 4 volt, the fan start turning. Now I'm at 46 degrees. That mean my temperature was set at 45 degrees. So this 20.05 kilo ohm means the fan will be start turning at 45 degrees. And now see what's happening at the voltage drop across the FET. The voltage drop across the FET is decreasing. It's no longer 12 volt. So when the fan is off, if I decrease it again, when the fan is off, the voltage drop across it is full 12 volt, full supply voltage, and the current is 0. Why? This is exactly how a switch works. An ideal switch to that matter. An ideal switch have a full supply voltage across it when it's open, and have 0 voltage drop when the switch is closed. Now let's see, as we keep on increasing the temperature to fully turn on this fan, and we observe that the voltage drop across the MOSFET is now almost 0. It's basically less than 1 volt, and you can see the fan is fully turning on, and the current flowing through here, through the fan, is now almost 1 amp of current. That means the fan is fully turned on, and the threshold voltage is way above 4. It's now standing at 5 volt. If you keep on increasing, thus you're going to see that this voltage drop across here is only going to go down, because the MOSFET is now going to be fully turned on. Now, just to demonstrate this concept of an ideal switch, our normal switch operate, I'm going to show you quickly one demonstration here. Now, to illustrate the concept of an ideal or a perfect switch or a real life switch, I've wired this simple series circuit. I've got an LED with a resistance and a switch, and I have a current meter to measure the current that's gonna flow, and a voltmeter. Now right now, if I turn this circuit on, you can see that the LED is not turning on. The LED is off, the switch is open, but the voltmeter is showing the full voltage, the full supply voltage across the switch. Why? Because the switch is open. That's an ideal switch. As soon as the switch is turned on, I've got 29.4 milliamps of current flowing into the circuit. The LED is on, and the voltage across the switch is now 0. Now, it's not really 0 volt because now we are measuring volt. Now, if I turn this circuit off and go into the settings here, change to measure millivolt, okay, and then run the circuit again, you notice that there is 0.29 millivolt that is dropping here. Now that 0.29 millivolt means there is some power that is being wasted here. Now you know that power is equal to V times I. So we have 29.4 milliamps of current flowing through the switch, and we got 0.29 millivolt of voltage. So you can calculate the power that is dissipating across the switch by multiplying this current times this voltage. Now you can have a lot of bad switches. For instance, let's pause this circuit again and increase the on resistance. So the on resistance is what set up the voltage drop across the switch. So if I turn this switch on again, you can see it's 0.29 volt. Now I'm going to increase the on resistance of the switch. Let's see what will happen. So I will make it 0.6 on resistance. Then I run it again. Boom. You can see I've got 1.7 millivolt. Is very small, okay? So you can multiply the 1.77 millivolt times 29.4 milliamps. You're going to have the power that is being wasted across the switch. Now this is still small, but if you are dealing with microamps of current and low power circuitry, this is very significant. And this is why it is very important to know your on resistance of your switch. If you have a high enough on resistance, that means your switch is not very good to run into a circuit, and that could be a bad contact switch and so forth, or a bad FET or something, or a transistor. Now, even though they say transistors, FETs, and they are good switches and so forth, but there's still going to be a voltage drop across it, and that voltage drop is going to result in power losses across the switches. So for instance, if this was a real application right here, we can see there is a 0.83 volt that is dropping across this FET here. Now, at almost 1 amp of current passing through the FET, if you have 0.83 volt dropping it, you can clearly see this is almost 1 watt that is dissipating here, because you can multiply, and that's almost 1 watt. P is equal to V times I. Now, this is very important, and this voltage drop is because of the on resistance of the MOSFET. Now, let's see what's the on resistance of this IRF. This is a simulation. On our real circuit here, we haven't been yet able to measure all of that, but if we can use multimeters and voltmeters and everywhere into the circuit, we can measure the voltage drop across it, the current crossing through it, and then from that we can deduce exactly how much power is this FET dissipating, and see how efficient is our switch. Okay, because we don't want the switch to wasting a lot of power when the switch is on. The switch must not dissipate any power when it's on. That's a characteristic of an ideal switch, but clearly we don't have a lot of ideal switch in a real world. Okay, now if we look at the data sheet of this MOSFET here, we can clearly see from the get-go we have RDS on. So that is the on resistance, the contact resistance for the switch. It says RDS on is equal to 0.85. So that basically means if you have 1 amps of current flowing through the MOSFET here, you're going to have almost 1 watt of power that's going to be burning there, just getting lost, wasted. If you have 2 amps, that's power just going to be increased. If you have 4 amps, 8 amps, and so forth, you're just going to have more power being dissipated into heat. This is why you have to mount them into heat sink to improve the efficiency so that they don't burn out. Okay, so this is going to be the end of this tutorial. I promised that we were going to do calculation, but the tutorial have gotten a bit too long. So in the final tutorial on this series, we're going to really determine what will be the resistance, that we can select if we want this thing to turn on 60 degrees, 45 degrees. We already see that 20 kilo ohm turns it on at 45 degrees. What if we want it to turn at 60 degrees? What resistance we're going to select? So that is this 20k resistor, 22k resistor we have here. So right now this one is turning it at around the same temperature there. So the next tutorial, which will be the final one, hopefully we're going to see how to calculate that resistance, and I'm going to breadboard this circuit to also use that resistance we're going to select, and hopefully we can see if it's going to turn at a higher temperature. Thank you for watching. Please stay tuned for the next tutorial. Don't forget to like this tutorial and subscribe to CMTEQ channel. That will be highly appreciated. I thank you. Till next time, cheers.